Hello. Over the next two videos, I'm going to be discussing line integrals. And you may think that the name suggests that these are the same as one-dimensional integrals that you've studied in the past and that we went over in the first section of the class. But actually, in the case of line integrals, what we're doing is integrating along a curve in 2 dimensions. We could also consider integrating along curves in more than 2 dimensions, but we're just going to focus on the 2-dimensional case, as with double integrals. And so there's 2 different kinds of line integrals that we will study. The first is line integrals of differential forms, which will be covered in this video. And the second is going to be line integrals with respect to arc length. So what are line integrals of differential forms? So as I said, a line integral is a one-dimensional integral but evaluated along a line or a curve in 2 dimensions. And the first type of line integral, the first flavor, is a line integral of a differential form, as I said. And so the integral takes the form that's shown here on the slide. And there are 2 things, well, maybe 3 things that occur in this formula. The first is a c, which is a curve, and it has to be an oriented curve. So we have a curve in 2 dimensions that goes through the plane, and we have to have a direction along the curve as well. And then there are these 2 functions, p and q. And we think of what's in the integrand here as a differential form. The fact that it has this dx and dy, this p dx plus q dy is a differential form. And so what we're doing is integrating this differential form along the curve c. And just to mention, these type of line integrals of differential forms come up in many applications. One example is the work that's done moving a particle within a force field. And so if we're moving a particle along a curve c, and these p dx plus q dy represents the force, p and q might be the components of the force, and this is the amount of work that you have to do, or the energy you put into the system by moving that particle along that curve with the given force. We're going to discuss this application in a bit more when we discuss vectors later on. And as I've already mentioned a few times, the other type or flavor of line integral is integration with respect to arc length, and we'll cover that in the next video. Okay, so what is this line integral of a differential form? So as on the previous slide, the formula for a line integral of a differential form looks like this. We have a curve c and a differential form, which is this function p times dx plus a function q times dy. And so, as I said, the line integral of this differential form has 2 inputs, the curve c and the differential form. And so we have this curve. One example of a possible curve is shown here. Of course, we could really have any curve in 2 dimensions. And in order to evaluate this line integral, the first thing that we have to do is to parameterize the curve. And so what do we mean by parameterizing the curve? This means that we introduce a parameter, I'm calling t here, which gives all the points along the curve. And so there's a parameter t, and then a mapping into the 2-dimensional space that gives the x and y coordinates. So a function x of t that gives the x coordinates as we move along the curve, and a function y that gives the y coordinate as we move along the curve. And t is called the parameter, and this function, mapping t into these 2 components, x and y, is called the parameterization of the curve. And just to give an example to hopefully clarify this, suppose we have that the interval here, where t is 0 to 1, and we're parameterizing this curve that's shown. And so at an initial time, t equals 0, we start at the left-hand side of this curve, and then as t increases, we move along to the right. And this motion would really be continuous, but I'm not showing a video in this presentation. So you have to think of this as being continuous, and we can just go in steps of 0.1. So when t increases to 0.1, we move a little bit and then continue to move along the curve. And this is the parameterization of the curve. And so at each point, we have the x and y coordinates along the curve, and that's the parameterization. Okay, so to evaluate the line integral, we have to introduce a parameterization of the curve. But then, what does it actually mean to evaluate the line integral? So once the curve C is parameterized by x of t and y of t, these functions of t, then we write dx to be equal to x prime of t dt. You can think of this as dx dt times dt if you use the Leibniz notation for the derivative. And dy equals dy dt dt, or y prime of t dt. And this is like the rule you use when you do substitution in a single integral. And once we use this rule for replacing dx and dy, then the line integral becomes, this line integral along the curve C of this differential form becomes just the single integral from a to b of p evaluated at the point parameterized by t times x prime of t plus q times y prime of t dt. And so what we've really done here is we've replaced this dx by x prime of t dt and the dy here by y prime of t dt here. And then this becomes then a one-dimensional integral, and we evaluate that using the normal methods that we know. Okay, and one key point about these line integrals of differential forms is that the line integral does not depend on the parameterization. So you imagine maybe you could have different functions, x of t and y of t, that still parameterize the curve, that still move along the curve, but maybe slower or faster. And in fact, this line integral does not depend on the way we choose to parameterize the curve. It only depends on the curve, the orientation of the curve, so which way we move along the curve, and the differential form, so and p and q. All right, let's look at an example and actually evaluate a line integral in an example. We're going to evaluate this line integral shown on the slide. So it's the line integral over a curve C, which is a portion of a parabola, I'll draw in a second, of this differential form x plus y dx plus x dy. And as it says on the slide, the curve is a portion of a parabola, y equals x squared. Here I've drawn the xy axes, and this curve is y equals x squared. And it's the portion of this curve that goes from negative 1, 1, this point, where x is negative 1, to the point 1, 1, this point where x is 1. Okay, and so how do we parameterize this curve? That's the first thing that we need to do in order to evaluate this line integral. So, discuss how to parameterize C, this curve C. And as I said, it is important which direction the curve goes. It goes here from the left to the right, so following these arrows. So we can parameterize this curve by simply introducing a parameter t, and let's say x of t equals t. So in fact, the parameter really is just the x coordinate. And then y of t, as we go along this curve, well, y has to equal x squared along this curve, and so it's x of t squared, which is just t squared. All right, and so what are the dx and dy that we should use when we use this parameterization? Well, remember, dx was x prime of t dt. X is just t, so x prime of t is 1, so dx is just dt. Y is here. Y of t is t squared, and so dy is y prime of t dt, and that is 2t dt in this case. Okay, so now we know what dx and dy is. We also need to know what interval t is in, so what is the interval t takes in order to parameterize this curve, and t is equal to x. It goes from -1 to 1. So the interval here is t in the interval from -1 to 1. And this gives us everything we need to know in order to convert this line integral into a one-dimensional integral that we can then evaluate. So it's going to be the integral from -1 to 1 of, well, x plus y. X was t, y is t squared, so that's t plus t squared. And dx was dt plus x is again t, and then dy was 2t dt. Okay, we could then factor the dt out, think of it that way, and so this becomes the integral from -1 to 1 of t squared plus 2t squared, so that's 3t squared, plus t dt. So now this is a fairly simple one-dimensional integral that we have no problem doing. So the indefinite integral is t cubed plus t squared over 2, evaluated from -1 to 1. And so when we evaluate t squared from -1 to 1, those cancel out. When we evaluate t cubed, we get 1 minus -1, so 2. So this line integral gives us 2. Okay, so that's our first example of evaluating a line integral of a differential form. I'm going to do another example with a slightly more complicated curve that we parameterize. The curve in this case will be the unit circle, as you can see. We're going to integrate this differential form over the unit circle, and we have to say which direction we go around the unit circle, because when we do a line integral, the orientation of the curve makes a difference. So we go around it anti-clockwise. So, doing the line integral around the curve C, which is going to be the unit circle in the anti-clockwise direction of this differential form y dx minus x dy. So let me draw the curve that we're dealing with in this example. The unit circle, here we have the x and y axes. And we have this circle, we're going around it in the anti-clockwise direction. All right, so how should we parameterize the circle? Well, there's always more than one way to parameterize, but with a circle, the very natural thing is to use the angle. So we start out with angle 0, and then we go to angle theta at some later time. This is much like using polar coordinates to describe points on the unit circle. And so we parameterize, in this case, the easiest thing to do is to parameterize using the angle. All right, and so when we do that, as with polar coordinates, as I discussed in the last video, you get that x of theta, now the parameter is theta, is equal to cosine of theta. It would be r cosine of theta in polar coordinates, of course, but r here is 1 because this is the unit circle. And then y of theta is sine of theta. Right, and then we have to know what are dx and dy in order to do this line integral. So dx is x prime of theta times d theta, and so that will be negative sine of theta d theta. And what is dy? dy is derivative of cosine with respect to theta, d theta. So cosine of theta d theta. And we also need to know the last thing is what is the interval that theta lies in when it parameterizes the unit circle. And so the angle goes from 0 to 2 pi once we've gone around the entire circle. So theta is in the interval from 0 2 pi. All right, so this is all the information that we need in order to evaluate the line integral, all the information from the parameterization, I should say. So this will become the integral from 0 to 2 pi of y dx, and so y is sine of theta, dx is negative sine of theta, so that becomes negative sine squared of theta, d theta, y dx, and then minus x dy, x is cosine of theta, and dy is cosine of theta d theta, so that's minus cosine squared of theta d theta. All right, so we factor out the d theta, and then we have minus sine squared minus cosine squared, which is minus 1. So this becomes the integral from 0 to 2 pi of minus 1 d theta, and that will just be minus 2 pi. All right, so this line integral is minus 2 pi. Okay, I'm going to do one more example of a line integral of a differential form. And in this case, the difference will be that the line or curve we integrate over is parameterized piecewise. And so the curve is shown on this slide. Looks like the graph of the absolute value, or graph of modulus, looks like this V. And we go from the left to the right. And we're going to parameterize the two pieces of the curve, the one on the left and the one on the right, separately. And when we do it this way, when we parameterize a curve, the two pieces of a curve separately, the line integral will simply be the sum of the line integrals of the separate pieces. All right, so in this example, I want to do the line integral over this curve C of x squared dx plus y squared dy. And, well, we already have this curve shown in the slide, but I'm going to draw it here so I can make some notations on it. So this is the curve, and this is the curve C, and I'm going to break it up into two pieces. The one on the left, which will be C1, and the one on the right, which is C2. This is kind of like when we did double integrals over compound regions, and we calculated the double integral over the compound region as the sum of the integrals over the individual regions. And so this line integral over the entire curve C is going to be the line integral over C1 plus the line integral over C2. So line integral over C1 plus the line integral over C2. And so we'll evaluate these two separately. So first, let's look at the line integral over C1. All right, so C1 is this curve. This curve, C1, is a segment within the line y equals negative x. So on C1, y equal negative x. And we can parameterize, as in the example using the parabola, by the x coordinate. We could actually parameterize by the y coordinate in this example, but let's use the x coordinate. Remember, in the parabola example, I set x equal t. And here I'm going to just sort of cut out that step of setting x equal t, introducing the other parameter t, and simply say x is the parameter. The x coordinate is the parameter. This simplifies things slightly. So we'll use x as the parameter. Okay, and so, well, dx is dx, and that's the parameter, and dy is going to be negative dx. So then we have dy equals negative dx, and y is given as negative x. And in this portion of the curve, C1, x goes from negative 1 to 0. Right, so this is all the information we need from the parameterization in order to evaluate the line integral on C1. So let's do that. Integral over C1 of x squared dx plus y squared dy is equal to the integral from -1 to 0 of x squared. X is the parameter, so we just leave that as it is. X squared dx plus y squared. Y is -x, so y squared is x squared. And dy is -dx, so dy, or dy here, becomes -dx. So we have the integral from -1 to 0 of x squared dx minus x squared dx. So these two cancel out. So this integral over C1 is equal to 0. Right, so the line integral over C1, this part, is 0. But we still need to calculate the part over C2. So let's do that. All right, so on C2, go back up to I can see the diagram. On C2, we have y equals x. And we'll use x as the parameter, just as in on C1. Use x as the parameter. Oops, sorry. Okay, and so when we use x as the parameter, in this case, we have y equals x, and so when we're integrating on C2, dy equals dx. And for C2, x goes between 0 and 1. Right, so that's all the information we need from the parameterization. We can now do the line integral over C2. The line integral over C2, we have x squared dx plus y squared dy. That's the differential form. And this is equal to integral from 0 to 1. X goes from 0 to 1 in this parameterization of x squared dx. X is the parameter, so this stays the same. Y equals x, so this y squared dx, y is the same as x squared dx. And so actually we have the integral from 0 to 1 of 2x squared dx. And we find the indefinite integral of 2x squared, that's 2/3 x cubed from 0 to 1. And so when we plug in 1, we get 2/3. When we plug in 0, we get 0. So this is 2/3. Right? And so the line integral over C1 is 0. The line integral of this differential form over C2 is 2/3. We add those together and finally get the line integral over the entire curve of x squared dx plus y squared dy equal to 0. That was the integral over C1 plus 2/3 or 2/3. So this line integral is 2/3. Okay, that ends this video. In the next video, we're going to discuss the other type of line integrals, which is integration with respect to arc length.